Today, so far, we've been talking about the importance of macular pigment. So I'm going to talk about ways to measure it in vivo, that's in the person, that's in your patients. So just a brief overview about what we've been discussing. Macular pigment is important. It has the anatomic location. It's located in the fovea, which is responsible for all your fine detail, central vision. It's a blue light filter and an antioxidant, which can help prevent age-related disease. So why should we measure macular pigment? So as we've discussed, it could be a potential predictor for risk of AMD. Now, with the human and economic impact of AMD in the world, which will be increasing with the increasing life expectancy, why not be able to reduce somebody's risk of this disease? Also, there's an influence on visual function and visual comfort from macular pigment. Studies have shown that vision under low light conditions and also glare conditions have improved with augmentation of macular pigment. So there's several different techniques to measure macular pigment in the person. All these techniques are very different, but as Shobha was talking about before, it's important to be consistent with how you measure macular pigment. So psychophysical measurements require subject input. Color matching and motion photometry have mostly gone out the window. Heterochromatic flicker photometry have superseded those, and customized heterochromatic flicker photometry as well. Physical methods require minimum subject input. Some people call them optical methods, and or sometimes objective, but we like to call them physical methods. There's resonance Raman spectroscopy, Fundus reflectometry, and Fundus autofluorescence. And I'm going to be discussing some of these techniques with you today. So the first one I'm going to discuss is customized heterochromatic flicker photometry. And I'll discuss, we use a research model called the macular metrics densitometer, but there's lots of clinical devices out there on the market. There's a few downstairs in the exhibit hall for you to view, ask questions about. So for this one, subjects are required to make isoluminance matches between a blue and a green wavelength. With our device, the target will appear flickering until that isoluminance match has been made. It'll then appear still to the subject. And we take that radiance measurement of the blue, and we calculate the log ratio of the radiance absorbed, the radiance of the blue light absorbed at the macula to a peripheral reference point. And then these are some of the devices. This is our research device. This is its baby brother, which is a more clinical, easier to use, faster. And this is the MPS, which is also downstairs. Some of the pros and cons of this technique. It's been fully validated. We take this technique as the standard that we compare other devices to and use in our own research. It accounts for ocular media absorption and scatter by use of that peripheral reference point. So if your patient has cataracts, it doesn't matter. You'll still get an accurate measurement. The device is relatively inexpensive, especially when you compare it to a lot of the optical devices. And there's no need for pupil dilation. Unfortunately, this method can be very lengthy depending on the method you use. Our method, which is very particular, can take up to 30 minutes. And also, it's difficult for some subjects to do, especially children, really old people, people with memory deficiencies. Resonance Raman spectroscopy, it takes advantage of the carotenoid's ability to exhibit Raman scattering. So we send in a wavelength of light, and when the wavelength of light hits the molecule, the carotenoid, it sends back a different wavelength that's very specific to the molecule. And this light can then be analyzed. Fundus autofluorescence exploits the lipofuscin in the retina. So lipofuscin is a fluorophore that's located in the retinal pigment epithelial down here. It's excited at a certain wavelength with peak excitation between 490 and 510, and it emits an autofluorescence that peaks between 590 and 630 nanometers. Now, macular pigment absorbs between 400 and 550 nanometers, with peak absorption at 460. And macular pigment is located anterior to the retinal pigment epithelial. Therefore, if you send in excitation light, if it's within the wavelength that is absorbed by macular pigment, it'll be absorbed before it reaches the RPE and before it reaches the lipofuscin. Therefore, the emitted autofluorescence of the lipofuscin will be attenuated by the macular pigment. So the device we use in our lab for autofluorescence is the Heidelberg Spectralis HRI plus OCT. It's a confocal scanning laser ophthalmoscope. It uses dual wavelength autofluorescence. So what this means is it takes 2 images at the same time. We actually take a 30-second video, which takes about 300 images. And it takes it in a blue wavelength and a green wavelength. And you can see here that with macular pigment, the blue light is attenuated, whereas the green is not. So it takes these 2 images. It takes about 300 of them, like I said, and then it aligns and averages each of them. And then you can see here, we have this dark spot in the middle. That's where the macular pigment's located. And then you can subtract the 2 images, and you get the amount of macular pigment you have in your eye. And this is what the output of that device looks like. You can see you get a full spatial profile across the retina. The pros of autofluorescence is it only takes several minutes to perform, little subject compliance, and provides a full spatial profile, as I was just showing. The cons is that the device itself is very expensive, and it requires pupil dilation. Subjects are exposed to bright levels of light, and the effects of ocular media is unclear. However, we're thinking about starting a research project that investigates the effects of cataracts on the Spectralis' autofluorescence method to see if there is an effect. There's several ways to measure macular pigment using fundus reflectance. Now, reflectance is the quantitative measurement of light reflected off the fundus. Now, you can either do a comparison of light reflected at the fovea to a peripheral point, and you can use either on the market, there's either single wavelength or dual wavelength reflectance devices available. However, the problem with a single wavelength reflectance device is there's no way for it to take into account any media opacities. Or you can do a spectral analysis of the reflected light using a broad spectral range. The pros and cons are much like the other optical method, the autofluorescence method: fast measurement time, little subject compliance, and provides you with a full spatial profile instead of just specific points like heterochromatic flicker photometry does. The cons, again, the device is expensive, requires pupil dilation, subjects are exposed to bright levels of light. With this method, there's also many assumptions and mathematical models, and the mathematical models often contain a lot of free parameters. And there's a need to control for intraocular light scatter by use of these mathematical models. So I'm going to go over some of the research that we're doing in Ireland. So the first study I'm going to talk about is we were comparing 3 devices for macular pigment measurement values. And these 3 devices were the densitometer, which uses customized heterochromatic flicker photometry, the Heidelberg Spectralis, which uses dual wavelength autofluorescence, and the Zeiss VisuCam, which uses single wavelength reflectance. And all these devices very different fundamentally in their methods, so we weren't expecting too great of concordance. But this is what we saw when we compared the densitometer to the Spectralis. So this is CHFP versus autofluorescence at several different eccentricities. And you can see at the most central eccentricity, 0.25 degrees eccentricity, we had very good concordance between the devices. Now, this concordance has not been this strong of concordance between macular pigment measuring devices has not been seen comparing devices that differ so much, which is important because optical devices may be easier than using an HFP device. And it also gives that full spatial profile, which may be good for research. This is the Zeiss VisuCam versus the densitometer, so it's reflectance versus HFP. And you can see here, no subjects measured above 0.5 optical density units using the VisuCam, whereas some subjects reached almost a full log unit on the densitometer. Like I said before, single wavelength reflectance is already flawed, and that's what the VisuCam uses. So in conclusion, we believe that the spectralis could be used in a clinical setting, also in a research setting, whereas the VisuCam should not be used, nor should a single wavelength reflectance device for the measurement of macular pigment. The next thing I looked at was the spatial profiles that were given by each device. Now, a typical macular pigment spatial profile peaks in the center of the fovea here, and we get this peaked mountain. But there's also been atypical profiles of macular pigment discovered, some that have a central dip in the center, such as a volcano, or a secondary peak at the side. So I compared the spatial profiles given from the densitometer and the spectralis, since their macular pigment measurements values correlated so well. I wanted to see if they also showed the same shapes. So the concordance between the two devices was in 80% of subjects. The spectralis showed more atypical profiles than the densitometer. So this is what a typical profile looks like. The top is the output we get from the spectralis. The bottom is the output we get from the densitometer, and you can see they both have this nice slope. The secondary peak, you can see this person peaks out here as well, as they do down here too. And this person has a secondary plateau, which also matches up very nicely. So the conclusion I got from this study is that there's very good concordance between these devices in both measurements and in profile classification. This study helps to confirm the presence of these atypical macular pigment spatial profiles. And as discussed before, macular pigment spatial profiles do have implications for macular pigment distribution in the back of the eye. And lastly, I'd like to point out, so these are from the same person, and you can see from the densitometer, you can see that they have a secondary peak. I mean, from the spectralis, you can see there's a secondary peak, but in the densitometer, it looks like they have a very normal spatial profile. So the spectralis is a little bit better at detecting these atypical profiles. So in conclusion, the need to measure macular pigment in the person, now that there's this growing body of evidence to support the link between macular pigment and risk of AMD, we could possibly start people before they even have signs of AMD. You know, you get that patient in who has family history of AMD, but they're 40, so there's no way they're gonna even show signs of it, and maybe they have a great diet, maybe they don't smoke, maybe they exercise regularly. You don't know what their macular pigment is like. I've measured tons of people that have come in, they say, oh, I eat lots of fruits and vegetables every day, but their macular pigment's suboptimal, which could put them at risk for macular degeneration. So why not start before they see signs of the disease? And also the influence on visual performance and comfort. If we could help, you know, young normal people that come into your offices every day who want to see better, why not see if there's a problem at the back of their eye, not just at the front of their eye? And that concludes my talk.
Have we any questions or comments for the measurement of macular pigment, or for Jessica? Yeah, Bill?
In our humble clinic, we found that autofluorescence is probably, from a clinician's point of view, the most repeatable, as opposed to, say, other commercial macular pigment screening devices. What are your comments there? Would you agree? Or?
I mean, we tested the repeatability of all of our devices, and they were all equally repeatable.
Valid,
Yeah, go ahead.
I think from the point of view of flicker, it's very important that you don't brand all flicker devices as the same device, because they're clearly not, and reproducibility clearly differs from one device to the other.
Sure.
And so my experience with the densitometer, this is the product from Professor Billy Wotton that was developed in Brown University, is that it's highly reproducible, it's highly accurate, and even now in the clinical version of that, the same stands up based on what we've seen. We've also looked at other flicker devices that have absolutely not been so reproducible.
But is there an advantage for getting rid of as much of the subjective component as possible when you think about the sorts of patient groups you might be clinically targeting?
Yeah, I mean, we could debate for a long time, and I'm sure Lisa and Randy might have a comment in terms of, you know, some of the challenges with autofluorescence and some of the still unanswered assumptions and questions. And they exist for every device. But to respond to your point, yeah, I mean, the more information you can get, the better. It's clear with flicker that we don't have 35 minutes in an optometry practice, and that's why you have these kind of commercial available devices that give you a snapshot of the central measure, which, as we've seen from some of actual Professor Hammond's work, is a very good predictor of what's going on elsewhere. So there's a lot you can learn from a good central measure, or even in now it's available that you can do 2 central measures. So I haven't answered your question, have I? It's the debate. Lisa, do you want to comment? You wanted to come in there?
Well, I think all that I would really add to it is, you know, there is some variability depending on who you're measuring as far as, you know, the different techniques that you use to acquire the measure. So the thing about psychophysics is always that, you know, you're asking a participant or someone in your clinic basically to make a judgment about what they're seeing. You know, you're changing the physical characteristics, they're having to make a judgment. And I think there is something that's pretty important to actually having the subject make a judgment. You know, you do gain information about what's going on with your person just by that fact alone. You know, as someone who's actually measured someone, you know, people literally across the lifespan, from very, very young, healthy folks to folks who have Alzheimer's disease and mild cognitive impairment, I will say that it's absolutely possible to get those measurements.
Oh yeah, we've done it, right? We've published work. We've collaborated on a project where we've been able to do it in AMD patients with customized flicker.
Right.
But yeah, I mean, it's a debate that I think is ongoing. Randy, do you want to add anything to that? I mean,
well, yeah, sure. So another point too is that just because something's subjective doesn't mean it's less accurate.
Yeah.
I mean, you know, humans can make visual discriminations that far exceed many physical equipment. So when you're measuring a subject who's, you know, got nystagmus or a dense cataract, these physical measurements are near impossible. But, you know, you have a brain in the back of your eye that's very good at correcting for all those distortions, and ironically, you can get more accurate measurements.
Yeah, I think the reason why you asked the question is I've seen what's happened in the UK with all these devices and a lot of them don't work, and there's been a lot of frustration and difficult, and I understand the frustration why that's there. I mean, one I suppose generic conclusions we can make is, and I think Jessica alluded to it, is absolutely, if you're interested in measuring someone over time, don't interchange, you know. There's certain, for me, there's some of the reflectance, the Zeiss Physicam that I've used, absolutely, for me it's not measuring macular pigment at all, and I wouldn't. It's a great fundus camera. You can get very nice retinal images, but I wouldn't measure macular pigment with it. So for me, scientifically, it's still the customized flicker photometry, and we have time and we spend time. The spectralis, I'm very encouraged by what I've seen with that, and clinically, so I think you have some options. Yeah.
Well, and as you sort of get used to working with these things, you know, I have to say that as someone who's been doing a lot of heterochromatic flicker photometry over the years, I get more information about the sort of health state of my participant often that way than I think that I would with an alternative method. So as I'm looking at their sensitivity to flicker, for example, I'm getting some indication of what's going on neurologically behind the, you know, sort of behind the photoreceptor, as much as I am, you know, what's actually embedded in the photoreceptor.
Yeah. Any last questions or comments? Yes, this lady here.
I'm quite sort of say the difference really between yourselves that are going into the research and the finer details of it, and a question that cropped up in one of the earlier sessions is how the individual is going to respond to if they are offered macular supplements, at the end of the day, they're going to judge as whether they feel their vision is better. And to a certain extent, whether one instrument proves a scientific point or not, the very fact that they have got an input to it, and it is a psychophysical judgment, that is what's all important to them. And when we're acting as clinicians, that's what we're trying to glean from them. Has it improved their visual being, their visual state? It might be misleading scientifically, but it's been a judgment for us and for them.
Let me ask a question. How many people in this room have measured macular pigment or would consider it? Let's who have measured macular pigment. I mean, so we're looking at maybe a third of the audience, which if we asked this question 5 years ago, there would have been no hands. So I think things have changed. Awareness is good here. I think the role of macular pigment is now being discussed. It's understood, and there's opportunities to go and measure this now. So that would be my recommendation. And we have some more, Stuart? Yeah.
Down 39% had atypical distributions with the spectralis.
Yeah.
So how did you define that atypical distribution? What was the degree of dip, and did it match your other published papers?
That was something that, I mean, there isn't really a standard right now as to what an atypical macular pigment spatial profile looks like. So it was done by visual assessment, but as I showed here, most of the people in the study is quite obvious. They're either, like this, or like this, or like this.
This was originally termed the ring-like structure, if you remember the paper on this. And it was a bit of a visual exercise. To answer the first part of your question, it did match our previous publications in terms of that. The significance of it, again, the conversation that needs to continue in terms of what this actually means. There's been several hypotheses. And,
you're leaning toward a 40% atypical.
well, I think
about 40% of people have an atypical profile.
I think Toss Bernschot's paper suggested that it was nearly as high as 50% of people, right. Which I haven't seen, and I know the lads haven't seen when we use Flickr. What we have to accept is with Flickr, I mean, I'm a big Flickr fan, and I will continue to be, but if you're not measuring at all these points, we have to make some assumptions and extrapolate lines and that. And what was interesting was this finding was that we would have said this is a typical macular pigment profile, but when we looked at it on the spectralis, because we weren't measuring at 0.75 degrees, we missed that point, we missed that plateau.
Right, so I mean the obvious, I'm putting on my clinical hat now, the obvious thing has to do with the concept of prescriptive carotenoids, that if we're able to measure precisely with patients with an atypical profile, we would want to supplement them with either Z-xanthin or meso-Z-xanthin or meso or Z, depending on what you think is going to work better there. But you would want to use a high-dose Z-xanthin isomer, right? I would suppose.
My view doesn't change on this, and we've discussed it this morning. I think if you're on the side of the fence that supplementation is important and the objective of the exercise is to increase macular pigment. Macular pigment is made up of 3 carotenoids.
Right.
Okay. My recommendation is use the 3 carotenoids that it's made
so
up.
So you're covering all bases.
Yeah.
Okay.
Can we get your mic, Randy, just so people can benefit from your comment? Thanks.
There's a man in the back that has a question too.
Okay.
So there was some interesting studies in the 40s actually that used. One thing about the macular pigment is it gives rise to several entoptic phenomena. One's called Heidinger's brushes, and another one's called Maxwell spot. So if you look at the original descriptions of Maxwell spot, and basically how you see these things is if you destabilize the macular pigment image, then you can suddenly see these entoptic phenomena. And in fact, a lot of people say that's why Charlemagne converted to Christianity, because he saw the Heidinger's brushes, which looked like a big cross, So, but the appearance of the Maxwell spot looks like a bullseye, presumably because of this, this trimodal profile. Yeah. But the trimodal profile itself has to also reflect the morphology of the cone axons. it's embedded in the axons, and they radiate spirally from the center. So it's reflecting some of that just the structural components of the fovea.
Yeah.
So that's why it was also suggested early on that you could measure these distributions to sort of as an assessment of these morphological changes over time. So early changes in the macular pigment distribution can also signal later pathology later on by looking at these cone changes.
Good point. And we have this gentleman at the back.
Can existing foods in the future be modified to give the daily recommended carotenoids, but only on a low volume intake?
Okay.
So you have spinach, but it just naturally contains 10 times the amount of its normal supplement. So the people are taking the substance without actually having to take excessive volumes of the stuff. So they're taking what's recommended, but they're not eating any more or not having to fork out any more money for supplements.
So you're on about food fortification.
Yeah, that's right.
Yeah.
So
It's
food's manipulated.
It's a whole other conference.
So you eat a pepper and it contains everything that you need. So it's been modified genetically to.
Yeah, it's a whole other conference. You know,
Right.
it's a whole other conversation. So I wouldn't claim.
So
to
people
have
are getting their supplements, but they don't realise they're getting it.
I mean, we know it exists. We know you have fortified milk, you have fortified butter. You can do it. Ice cream would be a very good food that you could fortify with carotenoid. You know,
but it must be a simpler, cheaper method than actually relying on a health system to provide the supplements, if they can actually put in the dietary things for people. So
yeah, I'm sure it's an area of opportunity, maybe.
yeah.
And we've Scott has a question. We might finish it at that then, and we'll move to the last lecture.
Hi, thanks for your presentation. And I think you're right. Macular pigment. I mean, I've got about 120 patients who've been measuring macular pigment over 7 years. When they see the change in the macular pigment, there's only 2 patients that I've ever put on a supplementation that their macular pigment score went down, right, for no reason I could find, right. But for everybody else, it goes up, and it's a really powerful thing for the patient to see that, because it also is a massive problem about compliance. You know, and why people should still take stuff. They might take it and get really excited at the start, but you've got to keep that excitement going. You know, so I think, you know, I'm a big believer in flicker. You know, I think you can use it rightly. So I think it's really important. The interesting about the fortify thing, I mean, what's really interesting is if you talk to GPs in this country, about 10% of patients can't eat tablets because they have dysphagia, and there was at one of the conferences recently, they've made a ARIDS-2 chocolate bar. Right? So that's crazy, because that was for the dysphagia patients. So I think it's fortified stuff is a bit another conference. But I think macular pigment is very important. Thanks.
Thank you, Scott. Okay. Thank you, Jessica.